Hello there, Mr. Sutton here, bringing you this AB Calculus 2.8 lesson on rate of change. In this one, we'll be finding the average rate of change of a function over an interval and the instantaneous rate of change of a function at a specific point. We'll also find equations of secant, tangent, and normal lines, and as a real-life application, we'll use the instantaneous rate of change to find the velocity of an object at a specific time. We'll start this one off with a few definitions. When I say secant line, we're talking about a line that goes through a function at 2 points, and the average rate of change, or AROC for short, is the slope of a secant line from one interval endpoint to another on a function. So basically this is the 2-point slope if you were to draw a line connecting one part of a function to another. So with that in mind, here's your warm-up. Given the function f of x equals x squared, see if you can find the average rate of change over the interval from x equals 3 to x equals 5. Give it a shot. All right, so let's see how that went. If we're finding slope, we're essentially doing y2 minus y1 over x2 minus x1. In function terms, the official AROC formula here, we've got f of x2 minus f of x1, basically just y values up here, over x2 minus x1. So as applied to this problem, we're doing f of 5 minus f of 3 over 5 minus 3. So that's going to be 5 squared minus 3 squared over 5 minus 3. So 25 minus 9 over 2. And then that's just going to be, let's see, 16 over 2 is 8. So 8 is our average rate of change on this function. A follow-up question. Write the equation of the secant line over the interval from x equals 3 to x equals 5. And just for consistency's sake, go ahead and use 3 as your x value on this. All right, let's see how that went. So maybe you remember to use the point slope formula, but if not, here's a good one for writing equations of lines. Y1, or rather y minus y1 equals m times x minus x1. It's a little bit better than slope-intercept for this because you just need a point, any old point. It doesn't have to be the y-intercept and the slope. In this case, our slope is this 8 that we just found. For the x and y value, the x1 and y1, I'm going to use the x value 3, and just plugging 3 into my function, that gives me back a y value of 9 because it's 3 squared. So I can write y minus 9 equals slope of 8 that we just found times parentheses x minus 3. Our next task is going to be to find the slope of x squared at x equals 2. So this is a little bit different than the last problem. I mean, how do we find the slope with just one point? So imagine that you have the slope of a secant line. Let's start there. So we've got x, and x plus h is my x values. This is just any old secant line. And I can write the slope of this as f of x plus h minus f of x all over x plus h minus x. Just normal slope formula. And we could even clean up this denominator a little bit to just be h down there. Now imagine that I'm moving the endpoints closer and closer together. So I've got x where it was, but now this h is getting a little smaller, moving a little closer, and my line is a little bit better of a representation of the slope down here. And let's say that I keep moving these closer and closer together until they're basically right on top of each other, and I've just got this line grazing the surface of my function. That line is called a tangent line. That's a line that grazes the function at just one point. And if you could find the slope of this, the instantaneous rate of change, which is what we're talking about with this 1-point slope, that would be the slope of that tangent line. So if you can find that 1-point slope, you've got the slope of your function there. So how do we do that? Well, I actually made a little Desmos thing to try this out. So here's my x squared function. Here's my secant line, and here's my little h value slider that I'm just making smaller and smaller, and here is the slope as I do that. So watch the slope, and you can watch the line too. So h is getting smaller, my line is becoming less secanty and more tangenty. H is approaching 0, we're almost there, our slope is at 4.1 now, and as we move to 0, the slope is undefined. If we move to a little bit before 0, the slope is almost 4. So it's looking like we're having some issues actually plugging in 0 for h, which makes sense. I mean, you essentially have 0 over 0 if you do that. So we can't just plug in 0. We actually have to write the IROC formula using a limit as h approaches 0. Then we can at least see where that slope is heading. At this point, we're going to use that IROC formula we just found, this one right here, to find the instantaneous rate of change at x equals 2 for the x squared function. Now, to use this, you have to plug in the x value, so this is going to be 2 plus h, and f of 2, and you also need to apply the actual function. So we're going to have 2 plus h squared minus 2 squared. All of that over h as h approaches 0. And we're going to simplify a little bit, because if you just plug in 0 for h, it's just 0 over 0 again. So this squared binomial, we can expand that to be 4 plus 4h plus h squared, and then we're subtracting 4. Now, it just so happens these 4's cancel each other out. And if we keep going here, it just so happens that everything has an h, which also can cancel out. So when the dust settles, we've got limit as h approaches 0 of just 4 plus h. And now if you plug 0 in for h, well, our limit is just 4. This is the instantaneous slope at x equals 2, the slope of a tangent line that we kind of approximated using Desmos. So this is how you could do it algebraically. So good news and bad news. Let's start with the bad news first. This was as easy as it gets. X squared is a very simple function. I mean, if this had just even been x cubed or x to the 4th, it would have been a nightmare to do the algebra. And what if it were sine or e to the x or ln, right? So this is a mess if you're trying to do it with anything more complex than this. The good news is we never actually ever need to do this long process to find IROC. We've got shortcuts for doing it that you're going to learn down the road. This was just showing you kind of how it could be done. So moving on then, we want to write the equation of the tangent line at x equals 2. So you've got the slope of the tangent line. Pause the video and see if you can get the whole equation. So for the equation again, we need an x and a y value, and we know that at x equals 2, the y value is 4 because we've got 2 squared. So using point slope, we're going to have y minus 4 equals our slope that we just found of 4 times x minus 2. So there's your tangent line equation. Now we want the equation of a normal line. And this is kind of a new word here. A normal line is just perpendicular, in other words, the opposite reciprocal of a tangent line that goes through the same point. So you need the same point as we had before, 2 comma 4, and you need the opposite reciprocal now of the original slope. So this is still going to be y minus 4, and now instead of 4, what are we going to have? Negative 1 over 4. You've probably done this before, it's just been a while. And then x minus 2 is going to be the same. We're going to do some more work with IROC, but before we do that, we need to figure out a few different ways of calling IROC. For example, when you see the word derivative, big calculus concept, this just means the IROC at a point or a formula for IROC at any point. Now, when you take a derivative, it's not called deriving, it's called differentiating. That's finding the derivative. And there's a bunch of symbols to represent this. There's actually 4 different competing sets of symbols. The big 2 are the Lagrange and the Leibniz symbols. The Lagrange symbols all use a prime marker. So if you want the derivative of f, you write f prime, and that's telling people that you're taking its derivative. Or you can have y prime, or you can just really have any expression inside of parentheses with a prime outside. These all mean derivative. Now, Leibniz also had some symbols, and these all have a d over dx kind of fraction-y format. For example, dy over dx, this is essentially the same as y prime. And you've also got d over dx of some function, or really just with any parentheses next to it. These all mean take the derivative. Now, in case you're wondering why this d over dx clunky notation is still around, it's actually kind of useful in some situations. The d, in fact, stands for delta or change, but it's a special kind of change. It's a very small delta. This is saying if you have an infinitely small change in y over an infinitely small change in x, well, that would give you the instant slope. Now, there's 2 different forms for writing derivatives with limits. So these, if we just write an f prime of x equals, these both are going to be equivalent. We have the Newton form, which you've already seen. It's this IROC formula here. Limit as h approaches 0 of f of x plus h minus f of x over h. Another way of writing this is using Leibniz's form, which looks like this. Basically, limit as x approaches a of f of x minus f of a over x minus a. These both are essentially doing the same thing. You have 2 points that are getting closer together, but Newton accomplishes it by just decreasing the difference between the 2 points to 0. Leibniz gets it done by just making one point actually turn into the other point. Now, in terms of what you need to know, you need to recognize both these forms on the AP exam. You never actually end up needing to take long derivatives like we did on Part C of that last problem, but you at least need to know these mean derivatives. And we're going to use a bunch of other techniques for actually taking the derivatives. At this point, we're going to get some practice expressing derivatives in limit form. So let's say the height of a baseball x seconds after being hit is modeled by this height function. We want an expression for s prime of x, the velocity of the ball. So essentially, you're going to take this and apply this Newton form to it, and you're going to leave x around because I didn't give you a specific x value to plug in. All right, let's see how that went. So we have a big fraction with an h on the bottom, limit as h approaches 0, and we're essentially just taking x plus h and x and plugging them into this function here. So we're going to write negative 16 x plus h quantity squared plus 48 parentheses x plus h, so that takes care of f of x plus h. And now minus f of x, well, f of x is just the original function here, so just stick all that in a parentheses and subtract it. We're going to do another one of these types of problems. I've just kind of worded it a little differently here. Write an expression for dy over dx for y equals 5 cotan of x plus e to the 3x. And just like the last one, don't bother trying to actually take the limit, just write it out. All right, let's see how this one went. So again, we're using a Newton's form here. I guess you could use Leibniz, but why bother? Half a dozen of one, 6 of the other. So here's our fraction, and now we're going to do 5 cotan of x plus h plus e to the 3 times x plus h minus all of that stuff. We're going to do one more problem, this time involving a table, which is a popular format for these things. Let's say we have a function and its derivative at selected values represented in this table. Find the following. So I want you to pause the video and see if you can get the slope of a secant line over the interval from 1 to 20, and then the equation of a normal line at x equals 7. All right, let's see how part A went. So for slope of a secant line, that's code for a rock. So we need to do f of 20 minus f of 1 all over 20 minus 1. F of 20 is negative 13. F of 1 is 30. So negative 13 minus 30. So that ends up being negative 43 over 19, which we can't really reduce, so we'll just leave it. Next, for the equation of the normal line, well, in general, we need to use our point slope form. So let's just write that out so that we have our shopping list together of things that we need to collect. We need a point, an x1 and a y1. They already gave us the x, it's 7. What's the y value at 7? Well, looking that up in the table, that's just negative 28. And now we also need the m value, the slope. The normal line, remember, that is perpendicular to the tangent line. So we need to start with the instantaneous rate of change, the instant slope. Looking that up in the table, that's what this f prime is telling us. F prime of 7 in the table is negative 5. So I need the reciprocal then, the negative reciprocal of negative 5. Putting it all together, I've got y minus negative 28, or y plus 28 for that y value. Now I'm going to have equals 1/5 for my slope, opposite reciprocal of the I rock here. And then I'll have x minus 7 for the rest of it. So that's it for this one. Feel free to pat yourself on the back and say I rock for making it through. Till next time, this is Mr. Sutton signing off.